Every year, all of us together, we put about 40 billion tons of carbon dioxide into the air. It pours out of tailpipes and smokestacks and furnaces, a flood of invisible gas, day and night, without pause. You would expect that to pile up in the atmosphere exactly as fast as we release it. So here is something strange. It doesn't. Go and measure the air, carefully, year after year, and you find that only about half of what we emit actually stays up there. The rest, year after year, simply goes missing. Tens of billions of tons of carbon dioxide, released into the sky and then quietly gone from it, every single year, for as long as we have been keeping count. So where does it go? It does not leave the planet. Carbon cannot just disappear. Something down here is reaching up and pulling half of it back out of the air, on a scale that matches the entire industrial output of our species. Two somethings, really. Two vast machines running silently in the background, and almost no one can tell you what they are. One of them is green, and it is all around you. The other is blue, and it covers most of the planet. Together they have been hiding half of our carbon for over a century, softening a problem we have barely begun to understand. But neither of them works for free, and neither one is guaranteed to keep going. So by the end of this, you will see exactly where the missing carbon goes, why these two machines have been doing us an enormous favor, and the quiet warning sign that they may be starting to tire. To find the missing carbon, stop thinking about it as pollution, and start thinking about it as plumbing. Carbon is not being created or destroyed, it is being moved, and it only has a few places it can be. Picture 4 great tanks. One is the atmosphere, the thin shell of air we breathe. One is the ocean, which holds far more carbon than the air does. One is the land, every forest and grassland and soil, the living world and the dead leaves underneath it. And one is the rock, the deep geological store of coal and oil and limestone, where carbon can sit locked away for ages. Between these tanks run pipes, and carbon is always flowing through them in both directions. A forest breathes it in by day and out by night. The ocean surface swaps it with the air across every wave. In fact, the whole living world inhales and exhales carbon so strongly that you can watch the entire planet take a breath once a year. For all of human history, those flows were very nearly balanced. Roughly as much carbon went into each tank as came out, and the levels held steady. What we did, starting with the Industrial Revolution, was open a brand new pipe. We reached into the slow rock tank, the one that nature kept sealed for millions of years, and we began pumping its carbon into the air, fast. The cycle was balanced. We put our thumb on one side of the scale. For a long time, no one actually knew if that extra carbon was staying in the air or not. The atmosphere is enormous, and a little more gas seemed like it might just blend in and vanish. Maybe the ocean was swallowing all of it. Nobody had measured carefully enough to say. Then, in 1958, a young scientist named Charles Keeling carried a delicate instrument to the top of a Hawaiian volcano, Mauna Loa, far out in the clean Pacific air. And he started doing one simple thing, over and over, for years, measuring how much carbon dioxide was in the sky. Two patterns came out of his data, and both were historic. The first was a wiggle. Every year the carbon dioxide dipped in the northern summer and rose again in the winter, a steady sawtooth. That was the planet breathing. The great forests of the north leafing out and inhaling in summer, then going dormant and exhaling in winter. He had caught the living world in the act. The second pattern was the one that mattered. Underneath the wiggle, the whole line was climbing. Relentlessly, year after year, the baseline crept upward. Before the Industrial Revolution, the air held about 280 parts of carbon dioxide per million. By today, that number is over 420. The Keeling curve became one of the most important measurements ever made because it proved the extra carbon was not vanishing into the air. At least half of it was staying, which meant the other half really was going somewhere. The hunt for the two machines was on. To find them, you do the accounting. You build a budget for carbon, the same way you would for money. On one side, what comes in. On the other, where it goes. Start with the inflow. Each year, human activity releases that roughly 40 billion tons of carbon dioxide into the atmosphere tank. That is the deposit. Now watch where it settles. If all of it stayed in the air, the atmosphere's level would jump by the full amount. It does not. Instead, the flow splits 3 ways. About 44% of what we emit actually remains in the atmosphere. That share has a name. The airborne fraction. It is the part that does not get hidden, the part that builds up and drives the warming. So where does the other roughly 56% go? This is the answer to the whole mystery. The land takes a piece, drawing down somewhere between 1/4 and 1/3 of our emissions into plants and soils. And the ocean takes a piece of its own, dissolving about another 1/4 of it straight into seawater. Add those two sinks together, and they are pulling down more than half of everything we emit. That is the favor. Without the land and the ocean quietly absorbing their shares, every ton we have ever burned would still be up in the air, and the carbon dioxide level would be far higher than the 420 we measure today. The two machines have been paying down half our carbon debt, on time for over 100 years. Now we can look at how each one actually does it. The green machine is photosynthesis, run at the scale of a planet. Every plant, every tree, every blade of grass pulls carbon dioxide out of the air and builds its own body out of the carbon. Leaves, wood, roots, the carbon in all of it came from the sky. And here is the strange twist. When you flood the air with extra carbon dioxide, plants on average grow a little faster and take up a little more. The land has been partly fertilized by our own emissions, and it has been absorbing more because of them. The blue machine is the ocean, and it runs on simple chemistry. Carbon dioxide dissolves in water. Wherever air meets sea, the gas pushes into the surface and gets carried down into the depths by currents and by sinking life. The ocean has swallowed about 1/4 of all the carbon dioxide we have ever released. But remember the warning from earlier. Neither machine works for free. When the ocean absorbs carbon dioxide, the gas reacts with seawater and makes it more acidic. Since the Industrial Revolution, the surface of the ocean has dropped about 1/10 of a point on the pH scale. That sounds tiny. It is a real and measured shift in the chemistry of the entire surface ocean, and it is already hard on corals and shellfish trying to build their skeletons. The ocean is doing us a favor and sending us the bill in acid. The land is doing us a favor, and we are clearing and burning the very forests that perform it. The machines are generous. They are not invulnerable. Here is the part that keeps carbon scientists up at night. And it is not the part you might expect. It is not really about how much we emit. It is about whether the sinks keep taking their half, because nothing guarantees that they will. Think about the land machine. A forest absorbs carbon while it grows, but a forest in a drought slows down, and a forest on fire does the opposite of absorbing. It releases everything it stored, all at once, back into the air. A hotter world makes droughts and great fires more likely, which means the green machine could start handing carbon back just when we need it to hold on. The blue machine has its own limit. Warm water holds less dissolved gas than cold water, the same way a warm soda goes flat. As the ocean's surface warms, its appetite for carbon dioxide slowly drops. The sink does not slam shut. It just sips a little more slowly each decade. And this is the quiet threshold the whole story has been circling. If the sinks weaken, our emissions do not even have to rise for things to get worse. The same 40 billion tons, with weaker machines underneath, means a larger share stays airborne. The airborne fraction climbs. More of every ton stays in the sky, and the favor we have leaned on for a century quietly gets smaller. Whether and how fast that happens is one of the central open questions in climate science right now. It is not settled. It is being watched very closely. Step back, and the carbon cycle is really a story about stocks and flows, the deepest idea in how complex systems behave. What you see on the surface, the rising line, the warming, is just the level in one tank. What actually governs it is the balance of the flows in and out, and the size of the hidden buffers absorbing the shock. And that shape is everywhere, once you know to look for it. A bank account is a stock fed by income and drained by spending. A population is a stock set by births against deaths. In each one, the level you measure hides a quiet tug-of-war between flows, propped up by buffers you cannot see. Carbon is the same, scaled to a planet. We started with a simple puzzle. We emit a flood of carbon, and only half of it shows up in the air. Now you know the rest of it is not gone. It is being held, ton by ton, in living wood and dark soil and cold seawater, by two machines that ask no thanks and take no rest. They have been balancing our books quietly for 100 years. The thing worth watching, the thing the scientists are watching, is not just the carbon we add. It is whether the machines that hide our half keep choosing to carry it.